Over to you, Graeme.
Okay. Thank you, Paul, and thanks for sticking around to the end. So like most people, I've made a slight change to the title of my talk. I put a question mark at the end of that decline question. So I like to begin these talks by reminding us all that modern biodiversity is so vast we've yet to basically take the register. So I went online earlier and found out that this is perhaps one of the newest species. So this is reported in the Daily Mail from a team from the University of Southampton has found this new ragworm species that's yet to have a formal name. But at the same time, perhaps the most sort of staggering conclusion from Darwin's origin is that all of this diversity ultimately goes back to a single common ancestor. And if we're interested in how we get between these two end members, what we really want to look at is the fossil record. And really, paleontologists have looked at two main measures to get at paleobiodiversity. So the first one is sort of classical taxon counting, taxon richness, and oftentimes people just use diversity to mean this. But of course, we've also looked at morphology and how that changes over time, often referred to as disparity. So what I'm going to try and do now is convince you that maybe we want a new metric, specifically phylogenetic diversity. I'm going to do this using an incredibly contrived example. So hopefully I don't have to work too hard to convince the people in this room that this sample on the left, exclusively of birds, is less diverse than the one on the right that includes a broader range of taxa, a broader range of ecologies. But if we were to use richness, we'd say these are equally diverse. They're both 5 species. And if we want to do something like morphometrics, we might say, well, I've got these skull landmarks for my birds, but I can't match them up to my crab or my jellyfish. But all taxa can basically be put in a tree, and if you timescale that tree, so the branch lengths reflect time, you can add up those branch lengths, and that's effectively what phylogenetic diversity is. And that will tell us the answer we want, that our right-hand sample is much more diverse than our left-hand sample. So biologists use this metric a lot. Here's an example using mammals from Fritz and Purvis in 2010. The scale here is billions of years. And we can see that phylogenetic diversity varies over space, and I'm interested in how it varies over time. So the limiting factor here is we need very large trees to do this. Fortunately, that's what I do. I build very large trees. So here's a recent dinosaur tree that's just come out in Biology Letters. So there's 960 species in here of Mesozoic dinosaurs. And I took the 100 trees to get a sort of phylogenetic uncertainty and the node dates from that paper. Then I took tip dates from the Palaeobiology database, and that's sort of the underlying empirical data. So before I show you that, what we want to do is set up some simple birth-death model simulations to give us an expectation of what we expect phylogenetic diversity look like, so we can compare real data to it. So here's a simplest null model. So birth is 0, death is 0. Phylogenetic diversity, therefore, will increase linearly over time, and the slope is going to be basically how many taxa you put in your tree at the start of the simulation. Then we did a bunch of different constant rate birth-death models, and these all give us essentially the same conclusion. So you'd get this sort of exponential rise in phylogenetic diversity. And then finally, we did diversity dependence. So there's a carrying capacity that's reached, and that means we get an inflection point in our curve. But the general pattern here is we expect a monotonic pattern. Phylogenetic diversity should increase over time. So it's kind of interesting then when we look at the empirical data so here we've got basically the Mesozoic, that dinosaurs for maybe the first 2/3 of their history, they do sort of follow this sort of exponential rise, so that's consistent with those constant rate birth-death models. But then something goes weird in the Cretaceous. They seem to have an inflection point, then they reach a peak, then they seem to decline over an extended period. We can also split out the various subclades of dinosaurs, and we see basically a similar pattern where the peak is can vary, other sort of issues with the shape, but generally we're seeing this decline consistently across the various subclades. It's not just one of them driving the pattern. So this seems to be consistent with a paper that came out earlier this year from Manabu Sakamoto and colleagues. They were looking at log node count over time, and they fit these models that suggested also a peak in the late Cretaceous, followed by a prolonged decline. However, of course, we have to be careful, and one reason we have to be careful is if we do a plot of effectively richness, number of lineages over time, we get basically a very similar pattern. If we do a Pearson correlation across 100 trees, we see they all fall out to the far right, so they're very strongly positively correlated. We can do the same for all of our subclades. And this is telling us two things. So first of all, it seems bad that basically our phylogenetic diversity is telling us the same story as richness, so why bother doing it? But also we know richness is going to be biased by sampling, so that makes us worry that what we're seeing isn't real. So the first point we can kind of alleviate by actually plotting out the number of lineages or richness effectively against our phylogenetic diversity. And when we do that, we see there's clearly non-random pattern in there. So that's telling us basically that richness isn't a really good predictor for phylogenetic diversity. In particular, it's going to overestimate phylogenetic diversity for the early part of the Mesozoic, so starting at the bottom, moving up through this part, and then it's going to underestimate phylogenetic diversity for the later part of the Mesozoic. And again, we split out the subclades, we see the same thing. So we can deal with this, though, and the sampling bias at the same time by basically subsampling, so we hold richness constant at 10 species in this case, throughout the Mesozoic, and then we can look at how phylogenetic diversity is varying independently of richness. So when we do that, what we actually get is more of a linear rise across there. So this is basically, looks like our null hypothesis model of that sort of with no birth, no death. And so our concern here should be maybe what we've done is thrown out too much signal and there's basically nothing left. This is like getting a flat curve in a subsampling regular taxonomic richness. But actually, this time we split out the subclades, we do see interesting patterns. In particular, we can highlight does seem to be a late Cretaceous decline in ornithischian dinosaurs, and we also get a mid-Jurassic decline in the sauropodomorph dinosaurs. So subsampling is getting at interesting things. But I also wanted to look at this decline in a new way. So I wanted to know whether or not it's an edge effect or it's real. So what I did is artificially created an end Jurassic mass extinction by throwing out all of my Cretaceous data. And then I'm basically hypothesizing there's two possible scenarios if we repeat all of the same analyses. The first one is that the signal is real. So we should see basically that rise up to the end Jurassic that we see in the total data set. But if it's actually an edge effect, we should see effectively the same kind of peak and decline we see in the full data set. So this is exactly what we do see with the real data. So we do have an edge effect seemingly. So we reach a mid-Jurassic peak once we throw out the Cretaceous, and then a prolonged decline to the end Jurassic boundary. And again, we can see this in all of the subclades. But what I also did is subsampled that data to see whether or not the subsample data is biased in the same way. Unfortunately, it seems like it doesn't, so it does keep rising to that end Jurassic extinction. And if we compare that to the full data set, the y-axes here are slightly different sizes, but hopefully you'll see the same sort of little bumps and a general overall shape in there. And again, this is true if we look at the subsample data, and we still, for example, get this mid-Jurassic decline in the sauropods. So overall, subsampling seems to be basically the way to do this. It seems to be robust against things like edge effects. So just to conclude, our expectations from birth-death models is a continuous rise in phylogenetic diversity. In real data, we actually find a decline, but it looks very strongly like this is more likely to be an edge effect. But subsampling is the way forwards, and we get two interesting patterns there. We can then think about what might explain them. So a decline in ornithischian and sauropodomorph diversity at different points of the Mesozoic. Thank you.